Oh no, I never did.
How empathy is related to
No, I don't I don't have time for this stuff.
Okay, we can start where we left off last time. We talked about what the thermodynamic basis need for editing in the case of the isoleucine tRNA and its strategy for getting rid of valine. And remember that while there is some preference, maybe 100-fold, for incorporating isoleucine into the tRNA, the isoleucine tRNA, in fact, the overall specificity for correct charging of the isoleucine tRNA is 40,000. So only 100-fold preference because of this methyl group isn't nearly enough to account for that. The other 400-fold coming from the editing. So the editing is the main strategy for getting the specificity that's required. And the experiment that indicated how important editing was is the experiment shown here. Valyl AMP, remember that is the activated form of valine that is required in order to allow this attack by the hydroxyl on the ribose to be energetically favorable. Valyl AMP, the charged valine, was mixed with tRNA, isoleucine tRNA, in the presence of the isoleucine tRNA synthetase. And what happened when these two were mixed together, well, somebody tell me, what does happen when these two are mixed together in the presence of isoleucine tRNA synthetase? What's the result and why? It's up there, of course. Yeah.
The valine is attached to the ribose in that.
In the tRNA.
In the tRNA, right.
Yes. What's the ultimate consequence, however? What did they see in this experiment?
Oh, that wasn't attached, right? The valine wasn't attached to the tRNA.
That's right. And beyond that, what did they see? This is a really neat experiment. Valyl AMP mixed with tRNA isoleucine in the presence of isoleucine tRNA synthetase does nothing more than just hydrolyze the valyl AMP to valine plus the tRNA, plus of course the AMP. Because, you know from this mechanism that we talked about, because what happens, as you said, is that there is an initial attack by the tRNA on the valyl AMP, which actually occurs quite efficiently. Not quite as efficiently as the isoleucine AMP, but still, this occurs quite efficiently, but because the valine is edited off by the mechanism that we talked about here, in the active site, in the editing site, they end up with valine and tRNA, just pure valine. So what is the mechanism that allows the synthetase to produce pure valine from valyl AMP? The first step, again, as you said, is that the valine gets attached to the isoleucine tRNA, and this is what it looks like attached This is the synthetase. This is the 3' end of the tRNA. And just as we saw for the DNA polymerase I, there's an editing site that can be entered into by RNA, waving back and forth. Now in the case of the polymerase, the editing site, notice the difference in strategy here. On the one hand, the strategy is fundamentally the same. When something is wrong, there is a way to make it very likely that the wrong thing, but not the right thing, will be edited off. In the case of DNA polymerase, it's fraying that allows the 3' end of the nascent nucleic acid to enter into the editing site. And it frays because it's incorrectly paired. So the polymerase has misincorporated a base, and because of that, it frays more easily, therefore is more likely to get into the editing site and get edited off. So in the case of DNA polymerase, the incorrect incorporation increases the likelihood of entering the editing site. Here, the editing site is constructed in a very special way to be specific. In the case of DNA polymerase, the editing site is completely non-specific. Correct nucleotides can be hydrolyzed off as well. It's just that the incorrect ones are much more likely to enter the site. Here, the site is constructed to admit isoleucine, but not valine. So after this occurs on the valyl AMP to produce valine-charged isoleucyl tRNA, that valyl tRNA can enter the editing site, but the isoleucine charged onto an isoleucyl tRNA cannot. Why? How would you construct an active site, an editing site, to admit an incorrect valine on the end of the tRNA rather than isoleucine? It's very, very straightforward.
Just make it small.
Yeah, make it small. Make it small. And you can see how easy it is to get specificity that way. You just make it too small to admit an isoleucine. Isoleucine can't get in. But valine gets in fine, so anytime a valine gets put on, it gets taken off. And so that's how this experiment works. You mix valyl AMP with tRNA isoleucine, and you get hydrolysis. That was a very interesting experiment because basically the isoleucyl tRNA was acting simply as a hydrolysis enzyme for valyl AMP. In effect, the isoleucyl tRNA was doing nothing more than just hydrolyzing valyl AMP. Okay, so they did a variation of this experiment. They mixed valyl AMP with isoleucyl tRNA synthetase, but left out the tRNA. What's the result of that experiment?
There was no hydrolyzation.
No hydrolysis. No hydrolysis. The tRNA is acting as a catalyst, in effect, because the tRNA is unchanged. It starts out free, and after hydrolysis it ends up free because this gets hydrolyzed off. So the tRNA isoleucine is acting as a catalyst, and the synthetase is acting as a catalyst. So there are two catalysts in this reaction. So there's lots of editing. I've talked about how important this is because this is the only juncture at which the code is translated. The only step at which the code is translated is the step at which the correct amino acid is attached to the correct tRNA. And so there's all kinds of editing that goes on. Now sometimes editing is not required. Some amino acids are so characteristic that it's possible to make recognition very, very specific from the get-go, like tryptophan, for example. Very unusual. There's no other amino acid that looks similar to tryptophan. But the isoleucine and valine, of course, are very similar. Here's another example. Threonyl tRNA synthetase. It has an interesting problem as well. Here's threonine. It also has a similar shape to valine. Only here it has an OH. And recognition can take place based on the hydrophilic, based on the hydrogen bonding characteristics of this OH, and in fact, based on its ability to complex with a zinc ion. So the threonyl tRNA synthetase has a zinc ion that distinguishes valine from threonine, even though they have essentially the same shape. Serine, however, is distinguished from threonine by editing. And hey, you can look at this and you can tell me with almost certainty how that editing mechanism works based on what we just talked about. So if it's not obvious to you already, think about it. The way to distinguish a serine from a threonine is conceptually almost exactly the same as what we just discussed for isoleucine and valine. Okay. So that's how the code is translated. You often hear that translation occurs on the ribosome. But of course that can't be true because this is the step at which translation really occurs and there's no ribosome involved. The charged tRNA then encounters ribosomes, and based on the anticodon of that tRNA, this is the 3' end of the tRNA. On this scale, the anticodon is down in the basement. The anticodon of this tRNA now finds the right codon on the messenger RNA, which is attached to the ribosome. And the ribosome completely mindlessly connects one amino acid to the next based on the association of the anticodons of the tRNA with the codons of the mRNA. And the ribosome just blindly trusts that each of those tRNAs, whose anticodon it's recognizing based on RNA-RNA base pairing, which is not translation, it just blindly has blind faith that each tRNA that it's accepting is carrying the right amino acid. So translation does not really occur on the ribosome. It occurs before the amino acid arrives on the ribosome. And this is just a brief sketch comparing bacterial and eukaryotic ribosomes. Just to remind you that the ribosome, whether eukaryotic or prokaryotic, has two subunits, a larger one and a smaller one. In the case of bacterial, 50S and 30S, larger in the case of eukaryotes. Everything almost is larger and more complex in eukaryotes because of the additional regulation required. Not because eukaryotes are bigger. This is a misconception that arises so often Well, eukaryotes are bigger, and so their ribosomes have to be bigger. That's nonsense, of course. Eukaryotes are bigger because they have much, much more sophisticated regulation. And the complexity required to sustain that regulation is reflected in all the components of the cell. The ribosome, for example, doesn't have bigger proteins associated with it, it just has more of them. So the ribosome is bigger to accommodate all the increased complexity of regulation that occurs during translation. So we're going to be talking initially here about the bacterial ribosome. So everything that in the next few slides is the bacterial ribosome. The messenger RNA is not shown in this diagram, but it goes through the hole here like this. And the 5' end is up on the top, the 3' end is down here. So imagine the messenger RNA going through like this. It goes through the hole, not over the 30th. And you see the tRNA diagrammed in here. This is based on actual imaging, the shape of the ribosomal ribosome here. But this is diagrammed in, obviously, but it clearly is intended to have the shape of the ribosome of the tRNA. So you can compare this shape to this. And remember, we've talked about this for some 1 or 2 times ago. There's an anticodon here. This is the anticodon end of the tRNA. This is the 3' end. We've been discussing in the last few minutes what happens at the 3' end here and the charging of each tRNA with the correct amino acid. But this is the anticodon end. So we're not going to be talking about the specificity involved in charging anymore. We're going to be going back to talk about the specificity at the 3' end, but I need to emphasize again that the specificity that occurs here in the ability of this to recognize an RNA is specificity of Watson-Crick base pairing. So we're not talking about translation, specificity of translation. We're talking about the specificity of standard Watson-Crick base pairing based on trinucleotide codon-anticodon interaction. So this is the anticodon here, and this is the 3' end, and you can see that there's a growing peptide chain here, which is exiting the ribosome through this exit channel. And you can see that the way translation works is that each growing peptide is transferred to the next incoming tRNA. You've seen this in previous courses, and we saw it a couple times ago in our introduction to translation. But it works by the peptide chain growing, and then the bottom of the chain gets transferred to the amino acid that comes in on each incoming tRNA. And so it grows longer and longer and longer, eventually coming out of the exit channel. This diagram shows the ribosome opened up sort of like a clamshell, like this. And so we have that ribosome opened up like that, and the one liberty that they've taken with this opening is drawing the messenger RNA and the tRNAs and the peptide chain in both halves of the clamshell to see how these are situated with respect to the 30S and the 50S subunits in the diagram up there. This is the 30S, and in fact, the messenger RNA binds initially to the 30S subunit. And the tRNAs, when they come in because of the mRNA, the ability to recognize codons on the mRNA. But the 3' ends dive down into the peptidal transfer center. buried deep within the 50th subunit. So the 30th subunit is binding the messenger RNA, guiding the incoming tRNAs to interact with the messenger RNA through codon-anticodon recognition, but to send this deep within the 50th subunit where the chemistry takes place. And what happens down here is ribozyme activity. The reaction is catalyzed by the RNA of the ribosome. When ribosomes were first characterized, it was assumed that the RNA formed some sort of a structural scaffold over which the proteins bound, and that the proteins catalyzed the reaction. We'll see in a moment that it's actually exactly the reverse. A very, very striking illustration of the role of the RNA world in facilitating the transition to the DNA and protein world. If you look from here straight down into the peptidal transfer center, this is what you see. So this is this. And you're looking straight down in there, and you see that when you look straight down, the RNAs are sort of at an angle. The messenger RNA is here, bound on the 30th subunit, but then they go down, and when you look straight down from the top, you see the E site, this is exit, the P site, the peptidal site with the peptide on it, and the A site, the aminoacyl site with a tRNA that has just come in with an aminoacyl. And you can see what's about to happen down here in the peptidal transfer center. These two tRNAs are bound in such a way that the business ends of each are pointing towards each other, providing for a very close approach here within the active site of the most recently added amino acid to the peptide, the growing peptide, and the new aminoacyl group coming in on the tRNA. And this peptide is transferred to that, and as we'll discuss, almost simultaneously the RNA shifts. The messenger RNA shifts with the tRNA attached, so that the tRNA that initially binds in the A site here shifts over with its newly acquired peptide chain into the P site. And then a new RNA comes in and sits here in the newly vacated A site, and so forth. And so looking down here, these are these two RNAs, and here's the exiting RNA, which has given up its peptide to the incoming RNA and has now moved on and is on its way out. We're going to be looking at all of this in quite a bit of detail from a mechanistic point of view. Here, the messenger RNA was not shown at all. Here it's shown diagrammatically, it's just a straight rod. But as you can see here, when the actual conformation of the RNA is taken into account, it's actually bound in a very irregular way, following a specific path on the surface of the ribosome that it travels as it travels through the ribosome, enabling the assembly of the polypeptide chain. Before moving to discussion of mechanism, let's just look at the ribosome a little bit more. This is mainly for you to look at later on to become familiar with looking at the ribosome from different perspectives, different points of view. Here is one where you're looking straight down on the tRNAs. So here you were looking straight down into the peptidyl-transferase center. So you're looking straight down into the peptidyl-transferase center, but the RNAs are sort of slanted in like this, and so you're seeing them in sort of I don't know what kind of a view you call that. They're sort of prone here. However, if you shift your perspective a little bit so that you're looking not straight down into the peptidal center, but that way a little bit so that you're looking straight down the axis of the tRNAs instead, then what you see is this. This is still the 50th subunit, and this is where the codon-anticodon interactions take place, are indicated by red. Here is the messenger RNA, and the codon in the messenger RNA that would interact with the P site is indicated right there. So again, you could close them up like a clamshell, and that's how they would interact. The active site is behind this shelf, down inside. This diagram shows the 50th subunit with bound puromycin, which is an antibiotic that we'll talk about, which mimics the aminoacyl part of or the peptidal part of a tRNA. But it doesn't recognize anything on messenger RNA, so it's an antibiotic because it causes peptidal transfer, but no mRNA, and so it short circuits the whole protein synthesis regime. We'll talk about that a little bit more when we look at the mechanism of elongation. In this view, there are no tRNAs. Instead, this is intended to emphasize the role of proteins in this overall structure, which is in fact mostly RNA. And remember, I said that initially, when people first characterized ribosomes, they thought that the purpose of the RNA was to form this great giant scaffold which would bind proteins in a very specific way in order to allow the proteins to carry out peptide synthesis. But now we know it's just the reverse. I mentioned that what happens down here is carried out by RNA. The catalysis is carried out exclusively by RNA. And the proteins serve a stabilizing function for the RNA. So instead of the RNA forming a scaffold for the proteins are stabilizing the RNA structure so that the RNA can carry out peptide synthesis. Very dramatic illustration of how the DNA and protein world evolved from the RNA world. Clearly, protein synthesis had to have occurred first in the RNA world because there were no proteins involved and no proteins around, obviously, in those days. So mechanism evolved for RNA to catalyze protein synthesis. And once the proteins became sophisticated enough to acquire many of the functions of RNA and then go beyond RNA, they then help to stabilize the RNA structure, but the ability to synthesize protein had been perfected already by RNA, and so that was maintained. And here all we have are proteins, and you can see they're diving into the ribosome, associating with the RNA in various ways to neutralize the phosphates. A structure like this with all of this RNA is obviously going to have a lot of negative charge that has to be neutralized. So the ribosomal proteins are quite positive in terms of their amino acid composition. Lots of arginines and lysines. And Also, the proteins stabilize secondary structure in the RNA. Little stems here and there, double helices, triple helices, and all of these things that we've talked about in RNA structure form based on the RNA's ability to recognize, but are stabilized by the proteins which bind to those structures. This view shows you a codon here on the messenger RNA on the 30S subunit, and you can actually see here how the RNA dives into, this is one of the best views for seeing how the RNA dives into the active site on the 50S subunit. And this structure emphasizes yet again that the connection of the amino acids to each other to form a peptide, and the recognition, the codon-anticodon recognition, occur in vastly different places on the ribosome. This occurs predominantly on the 30S subunit, and the chemistry occurs predominantly deep within the 50S subunit. And here is a full representation of the ribosome, with and without a bound tRNA, to show how the tRNA actually fills up this hole almost. So now, let's take a step back. We have a pretty good idea from all of this how synthesis takes place. So we can look at this experiment from the 60s, 1961, which asked a very basic question. But we can interpret that experiment from the point of view of our sophisticated knowledge now about how protein synthesis actually occurs on the ribosome. The question that was being asked here was, does polypeptide synthesis occur beginning at the N-terminus, going to the C-terminus of the protein? Or does it begin at the C-terminus and proceed towards the N-terminus of the protein? And so this illustrates the rationale. Suppose you start with ribosomes that have been isolated. I think this was probably done with rabbits. Suppose, I said I was going to be talking mostly about E. coli, but some of these things, the answers are universal, like N to C terminus. Ribosomes that were in the process of synthesizing protein were isolated. See, I've forgotten which protein this was. Hemoglobin, yeah. So we're looking at hemoglobin synthesis in the rabbit. Hemoglobin is a soluble protein, so think of how the synthesis takes place, because this is vital to being able to interpret this experiment. Where's the diagram I'm looking for? So hemoglobin is synthesized on the ribosome, and one amino acid after another is added. It's extruded through this pore, and when synthesis is complete, the hemoglobin comes out of the pore and diffuses away as a soluble subunit, which then meets up with other soluble subunits of hemoglobin, forming the final tetramer. And so ribosomes synthesize, in the process of synthesizing hemoglobin, were isolated. And of course, these ribosomes were these isolated ribosomes were caught in the act of synthesizing hemoglobin at all different stages of completion. Some were just starting a short peptide of hemoglobin. Others were almost complete, had synthesized almost a complete hemoglobin polypeptide. A few more amino acids and the hemoglobin would be released from the ribosome. They then incubated these isolated ribosomes with radioactive leucine. They incubated it with radioactive leucine long enough so that they could see the radioactivity by their detection method in their experiments, but never long enough to allow synthesis of a complete polypeptide chain. So they selected a relatively short time, not long enough to synthesize one complete polypeptide chain of hemoglobin. During the labeling period, however, any chains that were already almost complete would be completed and then released from the ribosome. But any that started synthesis would be unable to complete the synthesis during the time of the experiment. This is important because they are looking at the released hemoglobin, and they needed to know that all hemoglobins that were released were hemoglobins that were already in the process of synthesis on the ribosome, not ones that were started and finished during the experiment. So these incomplete peptides that were initiated during the time of the experiment, they don't see, because the way the experiment worked was after allowing synthesis to proceed, they removed the ribosomes and anything attached to them and looked only at the soluble hemoglobin that was produced during the time of the experiment. So these would all be removed with the ribosome, but these would be recovered as the soluble hemoglobin. Then they digested the hemoglobin that was released. After purifying it, they digested it with trypsin to produce peptides. And this just illustrates what a peptide map of a tryptic digest looks like using the techniques available at that time, which was paper chromatography. So they used paper chromatography in one solvent in one direction and another solvent in the other direction to produce this peptide map where each peptide migrates at a different position. The intensities vary a lot in these peptides because recovery of the peptides is notoriously variable. Some peptides are very hydrophobic and recovered poorly, others are very hydrophilic and recovered well, and all kinds of variations in between. So some are dark spots, some are very light spots, but that only has to do with how efficiently they're recovered during the experiment. So the rationale of the experiment then is that hemoglobin molecules that had been almost completed at the beginning of the experiment and were then completed with a short little run of radioactive amino acids and then released would be radioactive only at the end that was synthesized last. Remember, the goal of the experiment is to ask, does it proceed N-terminus to C-terminus? Whichever is last, N-terminus or C-terminus, is going to be the most highly labeled, because no matter how long the peptide was initially, it always gets labeled at this end when it's released. So all released peptides are labeled at this end, and so any peptide, any tryptic peptide produced will be labeled at the end that represents the end of synthesis of the protein chain. Furthermore, when you look at this, their rationale said you ought to get a whole bunch of peptides. This would be the most highly labeled, but peptides near the beginning where the protein was made would be labeled to very, very low specific activity. This means that they ought to be able to take and characterize all the peptides and rank them from least radioactive to most radioactive. And ranking them from least radioactive to most radioactive would indicate directly the direction of synthesis of a polypeptide. And in fact, they found that the N-terminal peptides were labeled very, very weakly, but the C-terminal peptides in this kind of an experiment were labeled very strongly. They actually did an additional experiment just to make sure that they had interpreted this correctly. They took the protein that had been isolated. This, by the way, is the amount of radioactivity or the specific activity of the peptides times the peptide plotted against peptide position. These numbers do not correspond to the direction, to the order of the peptides in the peptide chain. These numbers are numbers that correspond to the experimental method that was used to analyze the peptides. You can see here that the small numbers are here and the big numbers are here. So these numbers do not indicate the order of the peptides in the chain. And in fact, they didn't know at this time what the order of the peptides in the chain was. They wanted to do this experiment to confirm that they would be able to rank their peptides like this, and then this told them what order they were in the chain. But they still weren't completely sure whether this was the amino terminal or the C-terminal end, whether this was the amino terminal or the C-terminal end. And in order to determine that, they used the enzyme carboxypeptidase. Carboxypeptidase digests proteins one amino acid at a time, hydrolyzes proteins one amino acid at a time, starting at the carboxyl terminus. So if they were to take the hemoglobin that they had produced in this experiment and digest it very briefly with carboxypeptidase so that the last few amino acids were nibbled off of every one of these protein chains, and only then to purify what was left and do a tryptic peptide and analyze it, what they found was they got essentially the same answer, but these peptides were missing. These peptides were missing. That means that these peptides are at the C-terminus. And from that, they knew that translation proceeded from the N-terminus to the C-terminus of the protein. Yeah,
What's the black dot and effects that for the graph?
I'm sorry?
What's the black dot and effects that for the graph?
You mean what are the circles and X's for?
Yeah.
These are just repeated experiments. So you can see that there are many of them, and these, you have circles and X's, and they correspond to, I can't remember what the difference is in the experiment, but experiments were obviously repeated several times, and they were carried out in one way for the circles and another way for the X's, and the results show it doesn't matter how you do the experiment. They all give the same answer. Okay, so now we're going to start talking about the exact mechanism of polypeptide synthesis on the ribosome. you know what the goal is, to transfer this growing oligopeptide chain to an incoming aminoacyl tRNA, so that the peptide now is attached to this. So protein synthesis depends basically on taking a peptide and transferring it to an amino acid. The initiation of translation depends on creating, as the very first amino acid, something that looks like a peptide, so that once that is in place in the P site, it will automatically be treated as a peptide by the elongation phase of translation and transferred to the tRNA that comes in at the A site. So how do we get something that looks like a peptide to associate with the P site? Because in all of our talking about, well, let's go all the way back here. In all of our discussion, we've talked about how the RNA comes into the A site and then transfers to the P site. In fact, during elongation, the only way a tRNA can get to the P site is by associating first with the A site, and then the tRNA mRNA complex shifts over to the P site. So this is the only way during elongation something can get in. The rationale for initiation then is to assemble something directly on the P site that looks like a peptide. And then this strategy of bringing our tRNAs in through the A site, shifting them to the P site, can work. So we begin with a 30S subunit here, and there are a lot of initiation factors and elongation factors. Is my time up? I heard somebody say, yeah, I'll take your word for it. My time is up.